Hello, my name is Ortwin Hess. I'm a professor in the School of Physics and the Quantum Institute. And today I would like to talk about quantum nanophotonics. But before actually doing that, as a way of introduction, I would like to go and introduce myself and my team, and we have recently moved from Imperial College to Trinity. And this picture, taken in the summer of 2019, shows a bit of a different way how we interact today, because most of our COVID-related interactions now happen virtually. The way that we work together is through theoretical simulations and computational investigations of materials so that they could have and use quantum effects in light and matter. Some of those ways that we actually work is not so dissimilar from the way that architects would work on the nanoscale, so in order to design environments where this actually happens. And one of those environments that we recently designed, interacting with colleagues who then go and investigate this in an experimental lab, is, for example, the following. It's a rather simple design. It is one where a simple sphere, here indicated by this kind of collection of gold atoms, is at very close proximity to a surface, again made of gold. The very special thing about that is that the size of that sphere is incredibly small. It's just 50 nanometers, quite a number of zeros before you hit the meter scale. And at the same time, the distance between these spheres and the surface is even smaller, just a single nanometer. And now if you add a particular molecule, a quantum emitter, inside of that gap, which is maintained by a way of a different other molecule, well then, something very special happens. The way that light interacts with that molecule is very, very different from the way that it would interact normally. It shows quantum features. But one of the very questions how light can actually get into such small scales, that is related through the choice of the particular material by which we design these simple arrangements. In this case, the sphere is made out of gold, a very good conductor, and the sphere is also made out of gold. Because if you may remember, if you look at light, green light, it has a so-called wavelength distance between these troughs and the peak of a wave. They are about 500 nanometers. So how can I get anything of that scale into a gap which is a single nanometer wide? Well, there's the help of all those many electrons that live inside of that metal sphere. Light induces these electrons, like here in this little animation, artistically depicted, to oscillatory waves. And these waves, they behave in a not so dissimilar way, so-called plasmons, in the way that they interact with molecules. You can also, by changing the shape and the size of these nanoparticles, change the frequency by which they interact. So it's a kind of size design how the response of these materials work. Designing them appropriately allows us then to change the way that light interacts, to harness these quantum effects. But what are these quantum effects all about? Because quantum physics is one of the key and central elements of physics. This iconic picture, which is a little less than 100 years old, is from a conference where many of the giants of quantum physics actually came together. There's so many well-known names on that picture. Of here in the center, naturally, the quantum most well-known person perhaps is Albert Einstein or Marie Curie and Max Planck here in the first row. But it's particularly here Erwin Schrödinger, who left at the time when he was in Austria, but also at the time when he was in Dublin a strong mark on quantum physics. He came up with a way how to describe the reason for looking at this new type of physics was that there was felt to be something wrong with the way that we could understand atoms and molecules. Now he came up with a way how to describe and capture all of that in terms of a wave, and that wave was then described in terms of his so-called Schrödinger equations. He used his way of thinking also then to extend that to other fields than physics, like here when he, in these lectures that he gave in the very physics building here at Trinity, when he gave and just posed the question, what is life? Building the foundations for all these works that Watson and Crick later on did when they discovered the fact that there's a DNA strand behind the way that life is being coded. But Schrödinger did that, and the way that the quantum physics that was originally invented, if you may, in order to understand the properties of atoms and molecules, is now at the center of attention for some quite other ways in terms of a so-called quantum technology. It's not so long ago, just summer of 2019, where here's two headlines from the BBC webpage and the Irish Times, where Google announced that they actually obtained a so-called quantum supremacy, which means a computer built on working principles derived from quantum physics will be faster, better than the classical equivalent computer in that case. One can also already see that these processes here in this case seem to indicate quite a change in the way that things worked. But what is it, this way that quantum physics can be quicker? Our classical computers, and everyone knows that, are based on the so-called digital logic. It's one of the most powerful elements, seeing that either you have a state which is on or off, usually encoded in a 1 or in a 0, and by encoding information and encoding processes on top of that information, all of our computers, all of our mobile phones and everything works on this digital platform. In the quantum case, you also could imagine to have two things. A quantum state is now expressed in this, for example, in this spin 1/2 particle, can be either up or either down. But in quantum mechanics, it's not only being up or down, it's also every combination of being up and down, which is possible. So if you have many more combinations, you can see that you have many more chances to go and encode and operate with these. This is now a mathematical kind of bit of an overview of what could do. Mathematically is expressed what this wave function could do, being based on this mathematical, on this quantum state 0 and 1, how this is changed to a different quantum state. While this looks like a mathematical representation, it clearly has to go and have a way how it actually is realized as an inner physical system. This physical system, where this quantum chip that the Google team designed is based upon, here's the scale of about 10 millimeters, actually brings together a lot of these nodes that interact. It's based on a particular system called a SQUID, a superconducting quantum interference device, by which the states by which these different nodes interact are actually quite encoded. But one of the very particular elements in that is that in order to work properly, these elements have to interact and in an environment where they're shielded. Because if you can imagine something which is tiny and small and requires the description with a quantum from in terms of quantum physics, in order to maintain that interaction, you have to cool that down to cryogenic temperatures to reduce noise and fluctuations. But that clearly is a limitation, because you think that this so-called Josephson junction, where the electric charge and these Cooper pairs were being used, there's an opportunity that can build on this different geometry that I indicated before. Because if you look, for example, here at this two-level system, you can see that you can now have light and matter interacting together. So you have an absorption process where light, for example, being absorbed and elevated, and the molecule here in its state being elevated from a lower state to a higher state can absorb that light, but can also that state can also emit that state in a spontaneous emission way. And designing that this happens not in a classical way, where normally light and matter would interact only very briefly. Here now schematically depicted by charging the energy of light and the energy of where this transition in the molecule or in the atom would happen. They wouldn't do much with another. But in the case that we allow them to be squeezed in that tiny volume where they interact strongly, what started as light then takes on properties of matter, of the molecule or atom, and what started in its properties as a molecule kind of acquires properties that are more like in light. So this merging of light and matter on this very intimate way is the key element by which you can actually then transmit information in its quantum way from light to matter and back. And this merging of these liquids is a little bit perhaps illustrated by if you imagine that one of these liquids is tea, and the other liquid that you might add to the tea is milk. So if you first, for example, start with the tea being pure and the milk being pure, you add them together, they mix. And in your tea, you wouldn't expect them to demix again. But that's precisely what would happen if these two would be quantum in the quantum coherent state. They would be able to demix again and retain their information that they had before. And this is what is exploited. And this temporal picture of what happens in this case is retained, and it's normally very hard to achieve, is particular at room temperature where fluctuations are stronger than at cryogenic temperatures. But here, in this case, because they're sped up so strongly and you can see them, they are realized. So they form the basis for hopefully and expecting a quantum process which happens at room temperature, exhibiting these famous Rabi oscillations. The fact that this geometry allows molecules to be embedded in them. Also, there are other so-called quantum emitters which also can go and work along these lines. For example, a single quantum dot acts as a quantum emitter as well. They are the states that are involved are a bit more complicated or interestingly complicated and amplified in a particular way. What we've looked at there was to design an environment which looks rather different, but exploits, for example, the optical near field in order to obtain a quantum response of that quantum dot in its way that it interacts with light. So if we look, for example, at these two designed environments that then were experimentally realized, we can think about another level of how we could do that. And one which is perhaps very important, particularly at the moment, is by linking up, since we have allowed our processes to happen at room temperature, to linking up with a process which is more at home in biological processes. Let me focus on one of those, and in particular on the so-called immunoassay sensing. There's now a very schematic description of what happens in this sensing process. Because if you imagine that you would, for example, have a collection of antibodies, normally you would dress them and with antigens and then with other antibodies that have labels associated with them. And it is these labels that are actually then identified or detected. And naturally, if you remember that plasmonics, this science of tiny metallic structures being able to squeeze light in tiny little gaps. That would allow light to be much better to be connected with these labels if you do that already. So people thought about that. And naturally, this happened and worked by, for example, imagining that within that gap of these two hemispherical domes, representing in arrangements like that, you would embed something that you would like to go and sense. And if you would normally do that, you would then record a shift of a line that you would measure. Here in this case, it's the so-called scattering cross-section in dependence on the wavelength. So if a single one of those would be now embedded, but stressed not with just a label, but a quantum emitter, and in close proximity, something different could happen. Or rather, a similar thing could happen than happened here with the split of the peaks, saying that here now instead of just a shift and a split could happen. And this is highly more sensitive in the way that the measurement and sensing process can work. So in splits like that and sensing process like that, again, here shown in terms of the temporal oscillation, are opening up quantum effects to perform measurements, since they are now possible at room temperature, also in biological domains and other domains like that. So if you have these quantum emitters, not just a single one, but many of them, there's certain statistics involved, and through that, one can show that if one was to think about a classical process with a simple shift, some of them would be further away, some of them would be closer to the ideal condition in the gap. You would see a stronger or less strong, but if a split as a quantum signature and a classical one as a shift as a classical signature, you could see that even if you have fewer of those available, and some of them better placed than others, the classical response, here charted in terms of the so-called figure of merit, depending on the density, the number of them on that surface, being a quantum process, a single response has a similar magnitude as many, is independent of the density of that. And that's a very remarkable and very important effect if, for example, biological molecules such as viral distributions are to be investigated or detected. And with that, a quick summary. What I wanted to show today is that through theoretical and computational means, designing and understanding processes in environments that build on particular materials, where the materials processes are just as important as the quantum light processes and the quantum light matter interactions in them, we can design new situations by which we can propel quantum effects from cryogenic environments to room temperature, which is a huge step because it allows to go and build processes and use processes which do not depend on cryogenic cooling anymore, for example. It also allows to think about quantum processes in environments which really have to be at living temperatures, such as, for example, immunoassay sensing of living cell groups. So here, not only a huge enhancement, but the fact that they can be performed in the first place is a very, very important element in that. So with that, and a link to where more information might be available from the homepage, I would like to thank you for your attention. Thank you very much.